Hi, I'm Ann Muchler with Semiconductor Engineering. I'm here at Cadence with Frank Schirrmeister, and we're going to talk about hardware-assisted SoC development. So Frank, in the quest for smarter verification, can you run through some of the new use models?
Absolutely. If you look into an emulation or an FPGA-based setup, you have your emulator. So mine obviously looks like the Cadence one a little bit. So I have my Z1 emulation environment. And then you have in most instances a PC, a host attached to it. Actually, you have always a host attached to it with simulators running on it. And they are typically connected. The simulator does run in specific modes like the acceleration mode, for example. But now let's take the core use model first. The core use model is the user has his design under test or design under development, and he'll move it into the emulator and he runs it. He runs it faster, and one of the things people could consider between formal simulation, emulation, FPGA-based prototyping, the three dynamic pieces, simulation to prototyping, it gets faster and faster. But you also want to make sure that you're doing the items which have the best return on investment on it. So I have my DUT, let's say it's an accelerator of sorts, maybe some graphics accelerator. I put this into the box, into the emulator. So now I need to make sure that I can stimulate it right to get my design running. So people do different things. They do synthesizable test bench. We call that the STB mode, where everything is self-contained. This could even be, you really don't need this except for starting, stopping. Everything is self-contained in the emulator. You stimulate your design, you have the test bench built in, you run it all on the emulator. You could have a test bench over here, and this can be, so this is your test bench stimulating your design, so it interacts with the design. So now you can do the synthesizable test bench, you move it in here. In the other, what we call verification and simulation use cases, we run this one, the test bench on the host. So I'll take this away. Now I'm running into the test bench in the host, and it will stimulate the design which runs in the emulator. And I'm going back and forth with signals. I get faster execution than in pure simulation. So that's kind of qualifying as almost brute force. I'm putting an accelerator on it. These are classic use models. The third classic use model is what we refer to as in-circuit emulation. And what you do in the ICE mode is you're now not taking your test bench and map it in here. You're actually now taking your real environment. Let's say this accelerator talks to an Ethernet, or it talks to a MIPI, DSI, CSI. So I can now connect those as hard connections to, in Palladium world we have a T port here, and I plug an Ethernet port into my T port, connect that to the emulator, so the design under test can now be stimulated by Ethernet directly. So we provide a speed bridge to connect to the emulator, and I now pump data into my design. So the interesting thing is there is a virtual alternative on the other side, right? So we have the ability to also do these things in a virtual fashion for things like Ethernet, PCI, PCI Express, you can also have a virtual model, which goes over here. It runs on the host, and we call that virtual bridge. So this is called a virtual bridge, which is complemented over here by a real piece of hardware called the speed bridge. So where this pumps real data, like from a real Ethernet interface into the box, here I have a virtual adapter. So again, this can be Ethernet, this can be PCI Express, and there are more protocols under development. Here I'm virtually driving the data into the box and looking at the data, and here I'm getting the real data.
So Frank, what are some of the unexpected ways that you're seeing use models come up today?
Interesting. So I just came back from Embedded World in Germany. Our booth was right next to a couple of interesting testing booths, testing companies. Keysight, Axia, Rohde & Schwarz, Teledyne LaCroix. So those are not entirely unexpected. With some of them we are partnering. But what you find is that on the hardware world here, you may have a Rohde & Schwarz 5G tester driving real data into the design. In other instances, we're actually working with partners and partner companies right on the other side of our booth at Embedded World, where all the debug companies. So we have virtual connections going on for virtual debug, which will interface to tools from ARM, like the DS5 environment, or Lauterbach, the Trace 32 environment. So it's, and those also live over here with speed bridges. So when I talk to people at those companies, it was quite interesting. They said, we found new joint customers where I wasn't aware that they actually have an emulator that I knew, but that they then take the standard interfaces like a JTAG to attach the JTAG debugger on the host, either physically or virtually. Those are new things which are emerging, especially the virtual components here. So sometimes users do these based on standard open interfaces like JTAG in this case, do this by themselves without having to come to Cadence and Lauterbach or to really build this kind of in a custom fashion. They can just do it themselves because of the standard interfaces like JTAG in here.
So Frank, can you talk a bit more about what use cases are especially good for hardware-assisted development?
Yeah, absolutely. So we have use cases in here which involve software, which are typically the most specialized use models running on hardware acceleration, because it runs fast, it runs in the megahertz, or if I put the FPGA-based prototype next to it, things like our Protium, it runs even in the tens of megahertz range, right? So this is my FPGA-based prototype. As soon as I have software involved, I enable with those faster running machines a complete new set of use models. So that set of use models involves, for example, software development and software bring up. So there's software development on things like our Protium FPGA-based prototype. There's software bring up. We are working, for example, with our friends at ARM on things like connection of a virtual platform, which is completely at the transaction level, which uses the ARM fast models, for example. And that's connected to an emulation environment, and it allows you to boot an OS much faster, even though the megahertz speed wouldn't be fast enough normally. So with bringing those combinations in, you get to much faster execution. The other type of use models which also involve software there's low power in the context of software. So you have your software switching on and off the different elements in your design. So if your design has different components, different blocks in it, let's say this is your design just structurally, then you want to be able to switch all of these on and off. Well, for that, we have UPF, CPF descriptions on how to represent all this. And then what can be done over long cycles, over deep cycles in emulation, we can now see how the software will switch on and off the different domains in the chip. And for, this is UPF is 1, so this is a verification use model. There's also the dynamic power analysis, where I'm looking into the toggles as they're running here. So basically all the activity in my design, and I'm annotating back technology information to run power analysis. Last but not least, also in the context of software sometimes, but it's mostly driven by the defined stochastic traffic, is the notion of architecture analysis, where I'm taking my design with an interconnect, for example, map it into the box, and I'm looking at things like traces, things like transactions per second, and so forth. I'm basically running our interconnect workbench on top of hardware, and I can do it now over much longer cycles than I could do in simulation. So lots of interesting use cases. Those are all making use of the fact that you have long cycles possible, long traces possible. So that brings in things like software.
So is there a machine learning component to this, or does this intersect with machine learning or deep learning in any way?
Yeah, absolutely. There is a very distinct trend towards applying machine learning techniques, AI techniques, in this domain. So if you look at the amount of debug data I get out of my system, so this can be, if the emulator runs an hour, I have, I want to say, oodles of data, terabytes of data coming out, and you have really not enough manpower to look at all this that information yourself. So, meaning with a team manually looking at it, it's really constrained by the ability to look at data and debug data. So debug and then running regressions with lots of cycles is giving you data with big enough data sets that machine learning and AI algorithms actually will help you identify issues in your verification flow. So you look for things like, oh, last night after I checked in the latest version of my design, something fundamentally happened in my regressions which hadn't happened before, something I haven't seen before. So that's where AI and machine learning algorithms can be applied. Are we there yet? We were talking about at DBCon at a panel about the Alexa for verification. Not quite yet, but we are at the state where with debug information about regressions, we collect the right data on which things like coverage-driven analysis, regression-based analysis, finding which check-in of code caused regressions to fail, can apply these techniques going forward. So I think there's lots of more to come in the future.
So also I have to ask about automotive. Where does this play in the explosion of activity in automotive?
Explosion of activity in automotive. Automotive is a big space, especially in the ADAS domain, the whole infotainment domain. Things like software development, software bring up are very much happening in automotive. We have specific interfaces you need in automotive. So there's the automotive version of Ethernet with the AVB extensions. There are things like CAN and so forth which need to be supported. So it plays in that domain together then with, and that's really on a horizon, on a different axis, if you will, together with functional safety, where on the simulation side we are pretty far with formal and simulation. We are really far with fault analysis, and you can imagine this will extend for longer use cases like software, just like dynamic power analysis. Eventually people will want to do this in hardware-assisted development as well, figuring out whether when I run into a failure mode, whether my chip actually returns into a safe state of sort, or whether everything goes out of bounds, which it shouldn't in the case of automotive or air defense. So yeah, it fits perfectly in here for software development, for ADAS, for some of the connections. And then we actually have use cases from CDN Lives in which Bosch, as a tier 1 provider, talked about hybrid and how they use software to verify their IP. And then functional safety is a very big issue in this, where you can imagine going forward this to extend into the hardware domain as well.
Thanks, Frank, for telling us all the new use case situations with hardware accelerated development today.
Well, thank you for having me. This was great. Obviously, lots of interesting use cases today already. One thing which is often overlooked, hardware in itself is not just the faster simulator. These are all use cases which make increase your return on investment quite a bit, because it's enabling things which would not be possible with traditional engines. So interesting space, expect a lot of more use models to come going forward.